So I'm going to jump to my code where we can look at the rolling average, the Hann window and that Hamming window. Before I just jump to the code, I just wanted to say that I'm going to be using some functions from the SciPy package. They're in a signal processing library within the SciPy package. It's called Signal. And in that library is a number of tools that are very useful for signal processing. So one thing we'll use is a function convolute. And convolute will allow us to do the rolling average filter. Because the rolling average filter is really nothing other than convoluting your input signal with some sort of rectangular box over which you're sampling the input signals. So we'll use this function here in my code. Then there's two other functions that I'm going to use out of that library, and they're just functions that handle this Hann window and this Hamming window. So the Hann window and the Hamming window have, as you saw, they're kind of bell-shaped curves. One of them, the Hann window, is a bell-shaped curve that falls to 0 at the edges of the window. The other one is the Hamming window, is a bell-shaped curve that doesn't quite fall to 0 at the edge of the window. The reason for the difference is that actually the one that doesn't quite fall to 0 has the fastest fall off of the frequency attenuation, although overall at high frequencies, the one that does have the fall off has a greater attenuation. So in certain circumstances, you might want a Hamming window, in certain circumstances, you might want a Hann window. But anyway, they're both in that signal package within the SciPy library. So here's the Hann, and here's the Hamming. And basically, in all three of these functions, right? So convolute will be a rolling average. Hann will be a Hann filter. Hamming will be a Hamming filter. You give the function in the library your input signal, and you'll give it your the size of your rolling average window, or your Hann window, or your Hamming window. And then it will do the convolution. It will calculate the output. Okay, so here's my code. I'm going to make basically sine waves or sinusoidal signals. I'm going to make them with a number of different frequencies, actually, and then we're going to feed them into our filters, the rolling average filter and the Hann and the Hamming filters, and we're going to look at the frequency response. So look at the amplitude of the output divided by the amplitude of the input, and that will characterize the frequency response. So I'm going to go ahead and do that. So you can see here that I'm importing, I want the this signal package in SciPy, and I'm also going to import the Fourier transform package, so we can look at the signal in frequency space as well as in the time domain. And then I want to do some plotting, so I got matplotlib. Okay, so this second cell, the first two quantities here are just going to define my discrete kind of space, my discrete time coordinates. So I'm going to think of time steps of 1 second. So I digitize my signal on 1 second intervals, and I've got 1,000 of those steps. And then I'm going to define a signal, a sinusoidal signal with a certain amplitude and a certain frequency and a certain phase. And so that's going to be my sort of test signal. And actually, as we walk our way through the code, I'm going to be changing the frequency. We'll vary the frequency so we can find the frequency response. But right here in this first cell, I just define a single amplitude signal, single frequency, and single phase. And then in this cell here, I'm just plotting that. So I make my array of times, n times, with a size dt. I'm going to make my sinusoidal input here. So here's the amplitude, here's the sinusoidal signal, here's the frequency, here's the phase. And then, just for purposes of plotting here, I made a Fourier transform of that input signal in these two lines here. So I'm calling these packages that give me firstly, FFT gives me the Fourier transform. We met that before. And FFT frequency gives me the x-axis for the frequency domain. And then I'm just plotting these two things. So here's just an example of a signal that I'm going to put into my filter in the frequency, in the time domain upstairs here. So you see the sinusoidal signal, amplitude of 1. It's got a period that's 20. That corresponds to the frequency I said. And then here we see it in the frequency domain. So in the frequency domain, it's a nice pure signal. The frequency is 0.05 hertz. Okay, so that's basically what I'm going to be working with. So in this cell, I'm actually going to calculate the frequency response of the filters. So this is, I'm going to calculate the gain as a function of frequency for the filters, and I'm going to do it for several different window widths. So I'm going to have actually nested for loops here, because I want to scan frequency and measure the gain of the signal coming through the filter, and I want to change the number of samples in the filter, and so I need 2 for loops for those two axes. And so upstairs here, these first 3 lines, this is where I'm going to set the range of windows that I'm going to use. And then in the second group of 3 lines, this is where I set the range of frequencies that I'm going to use. So let's start with the frequencies. I'm going to start with a minimum frequency of 0.00 hertz. And then I'm going to increase that in 0.001 hertz steps for 500 frequency steps. So this will step me up to 0.5 hertz. So that's my frequency range. And then for the window range, so this is the number of samples in the window, it's these parameters here. So in this case, I'm going to start at a window that has a width of 11 samples, and then I'm going to increase that 10 samples at a time for 3 steps. So I'm going to do a width of 21 samples and a width of 31 samples for my window here. These are all odd numbers. I'm picking odd numbers for the the width of the windows, because when we look at one sample on the input, so that's one sample in our window, and then we want a equal number on either side. So I'm going to, so for example, if I got 11, one of those samples is the sample in the middle, and then I got 5 on either side. If I go to 21, one of the samples is in the middle, then I got 10 on either side. So that sort of pattern. Anyway, so this is my range of windows, and this is my range of frequencies. I defined here a few arrays that I'm going to use as in order to make the frequency distributions and the gain distributions. So the array xi is just going to be the array that holds my signal with my different frequencies. The array frequency, this array frequency here, is just going to hold the various frequencies of the signals that I put on into the input. And then this array gain, I'm going to fill that as I go through these nested for loops to when I calculate the gain as a function of frequency. So ultimately, I'm going to be looking at the gain versus frequency that comes out of these two arrays here. There's two other parameters. I'll mention those, x low and x high. I'll mention those in a minute. But anyway, for now, this is just initializing an array to hold my signal, that's xi, an array to hold my frequencies, because I'm later going to want to plot it, and an array to hold my gain that I'm going to calculate, and I want to plot those. So it's just initializing arrays, basically. Okay, then we go down here. So as I say, I'm going to go through two loops. There's a big outer loop where I've got these three different window widths. So I'm going to go 11, 21, 31. And so we're going to explore those three window widths. And then I've got an inner loop, kind of the tight inner loop, where I go over the 500 frequencies. So I really scan the frequencies from essentially 0 frequency up to about half a hertz. And so those two loops have these two integers for the window loop and the frequency loop. And so inside that nested loop, what do? Firstly, I make here a signal of the given frequency. So every time I go through this nested for loop, I'm going to change the frequency. I'm going to increase the frequency and explore the response of the filter. So the first thing I do is make the new frequency with this little statement here. I have to make the window that I'm going to convolute that frequency with. So in the case of the rolling average, that window that I'm going to convolute the input signal with, supposing it would be the input signal was the window was going to be 3 samples wide. It would be an array of 1/3, 1/3, 1/3. That's going to average over 3 samples. If I'm going to have a window that's 11 samples in width, then it's going to be an array of size 11, and the values in the array are 111, 111, 111, so on and so forth. And likewise, if I want an array of, if I want to have a window, there's 21 samples, it's going to be an array of 21, size 21, with 1/21 as every element in that array. And so that's all I'm doing here with this little statement. This is just building that array. So I'm just this repeat function just generates copies, this number of copies of this array here, and this number of copies here is just my window width. Okay, So then here's the line that does the convolution of the window. So the convolution of the window with the input signal. So this is where I call that convolve function in that signal package in SciPy. And so in that one line, I do the windowing. So if you look here, I'm inputting the signal and I'm inputting the window and it's returning the output. So this is like imagine this rolling average, some sort of black box in this function. I'm putting in the signal. I'm telling it what is the window, and then it's giving me the output here. So Xi goes in, Yi comes out. What we want is the gain. So what I've got to do is I got to look at the amplitude of the signal on the output and compare it with the amplitude of the signal on the input. Where the amplitude of the signal on the input was 1, we simply called it 1, defined it as 1. But the amplitude on the output, I've got to inspect that sinusoidal output. And so there I'm using this function A max, which will tell me the maximum value of Yi. So this will be the amplitude of the output signal. And since my input signal had an amplitude of 1, this will be the gain. So this is how I get the gain. There's one subtlety there that you might bump into, is that at the beginning and the end of the digital signal, there will be transients in general, because you don't have samples before the beginning to average, for example. So at the beginning, there will be transients in your output. And so you want to kind of bookend your digital signal to remove transients at either end and just look for the average in kind of the central region. And so that X low, that X high, in this case, I need X low, I don't need X high, but I bookended both ends to remove the far left and far ends of the digital output to get myself away from any transients related to the beginnings or ends of the signals. And so that's why I'm slicing just this middle piece of Yi. Okay, so this calculates the gain for me, and here I'm just storing the frequency. And then finally, I'm going to make a plot of frequency of the gain versus the frequency. And I'm making this plot inside the loop of different windows. So it's going to show me the gain versus frequency for each of the different windows that I'm running with. And in this case, I'm running with 3 windows. So let's run this. And so this is the final output. So this is just a plot generated by this line of code here of gain vertically. So this is gain. It can be as large as 1 versus frequency horizontally. So the frequency we scan from essentially 0 hertz to half a hertz. In this plot of gain versus frequency, there are 3 different colored curves, and they correspond to these 3 different windows. And so we had a window that was 11 samples. That was our smallest window. We had a window that was 21 samples, and a window that was 31 samples. So if you think of the window 11 samples, that will have the property that every time you have a period that's exactly 11 samples, then that frequency will be eliminated, completely attenuated. If you have a window that is 21 samples, then every time you have a frequency that corresponds to a period of 21 samples, that will be eliminated. And then if you had a window that's 31 samples, so that's the longest period, every time you have a frequency that corresponds to 31 samples, so that will be the lowest frequency, that will get eliminated. So if you look here, look at if you walk along the horizontal axis, so from low frequency towards high frequency, if you walk along that axis, you see zeros in these different frequencies here, and these, or not exactly zeros, but vanishing gains at these particular locations, and that's where the window is kind of matching the period of the particular frequency that you're trying to drive through that filter. So you get this pattern of peaks and troughs, which is where your frequency at the input kind of either exactly matches the width of your window, or where the frequency at the input doesn't match the period of your window. So that's these patterns here. You see that, so the narrower window has kind of a higher frequency cutoff for high frequencies. So when you have a narrow window, higher frequencies can get through that window. And if you think about the limit, if you had a window that was just 1, everything gets through that. So as we turn the window up from 1 to 3, we start to cut higher frequencies. As we turn from 3 to 11, we cut even more frequencies. As we go from 11 to 21, then 21 to 31, which we're doing here. As you go from blue to orange to green, you're cutting more and more frequencies out of your spectrum. And so sort of the patterns of the minima, as when you either match your window width or you mismatch your window width, and the general sort of amount, the overall sort of frequency cutoff between low frequencies and high frequencies kind of makes sense. Okay. Let me show you a different window. So let's try and remember this picture of this frequency response of this particular rolling average filter. So that was the simplest filter we could sort of conceptually think of. And then I'm going to remove that, and I'm going to call instead. So instead of making my window with this repeat function here, I'm going to make my window with this function that will give me a Hann window. So this is one that is it's not a uniform window across your n samples. Rather, it's peaked in the center and falls off to 0 at the edges. So it has a different weighting. And so because it has a different weighting, we're going to get a different frequency response. If I run this one, so this is the frequency response with the Hann window. So you see the same general features in this as we saw in the rolling average. So those general features are, look at the valleys here in the blue curve, or in the orange curve, or in the green curve. These are where you're kind of matching or not matching the size of your window, but it's not exactly like that anymore, because your window is a not an even weighting. But anyway, if your period of your signal tends to match the window size, then it's going to be attenuated. If it tends not to match the window size, then it's going to leak through. And so that's these patterns. They're more closely spaced for the window of 31 because that's a wider window. It's a lower frequency, corresponds to a lower frequency. So you get more of these valleys. It's more widely spaced for the window of 11 because a period of 11 is a larger frequency. And so in frequency space, the spaces between these minima is larger. You also see the same feature. If you look at low frequencies, right? The window of 11 lets more through more higher frequencies. Its cutoff is higher. The window of 21 is lower than that. The window of 31 is lower than 21. It has the strongest cut on high frequencies. So that's a Hann window, and it's hard to remember the previous plot of the rolling average, but this attenuates higher frequencies more rapidly than the rolling average one. And then the other one I wanted to show you, which is commonly used, is I'm just replacing the creation of this Hann window, so a particular window shape for a particular window width, with the creation of a Hamming window, which is a particular window shape with, again, a certain width. The difference between them, mainly if you look at them, the difference you'll notice is that the Hann window falls to 0 at the edges, and this one doesn't fall to 0 at the edges. And it's picked, you'll see it here. So it's picked because it really has the sharpest fall off of the frequency response as you raise the frequency of your signal to a level. I mean, there's ups and downs in this level, but it's a rather constant level at high frequencies. And so if you think about this a little bit, this is a reduction. This filter is filtering out high frequencies at the level of a part in 100 or a part in 1,000. So it's a very effective filter. It's much more effective than the RC filters, low pass filters that we discussed.